For almost 60 years, graphene has been known as the wonder technology of the future. This is because it has many superlative attributes that cannot be touched by any other material. Some of these attributes include being the thinnest imaginable material at only 1 atom thick, being 200 times stronger than steel, having the largest surface area at 2,700 meters squared per gram, being even more conductive than copper, and finally by being completely impermeable, where even helium cannot squeeze through it. For a very long time, graphene was purely theoretical because it could not be produced. Now I'm going to talk about the history of graphene. So graphite was discovered nearly 500 years ago as a naturally occurring mineral. For a very long time, graphene could not be isolated because it's only 1 atom thick. The technology at the time prohibited scientists from determining whether they had actually achieved graphene or whether the graphite was still a few layers thick. In 1948, two scientists, Roos and Vogt, used electron microscopy to show that they'd actually achieved a few layers of graphite, and then a few weeks later, they finally narrowed it down to one single layer that is 1 atom thick. It wasn't until the 1970s that scientists were able to attach these single layers to other materials, in which way they were able to discover the properties that the graphene possessed. In 1986, the scientists Bohm and other helpers recommended the term graphene be used to describe the single layers of graphite like carbon. After that, there was a lot of research done to discover a way to make mass quantities of the graphene, but nothing could be found. Ultimately, it was the simplest approach that led to the first isolation of a single layer of graphene in 2004 by a Manchester University group led by Dr. Geim. It's called the Scotch tape method because the scientists used Scotch tape to successfully remove layers from a graphite flake. Even though the flakes present on the tape are much thicker than one layer, we can use van der Waals attraction to the Scotch tape to delaminate the single sheet when the tape is then lifted away. After folding the Scotch tape about 10 times, the graphite will be so thin that it'll lose its shiny sheen. Then the graphene will be placed on an oxidized silicon wafer to see it better under a microscope. After a great deal of practice, this method can result in high-quality crystalline structures that can be over 100 micrometers squared in size. The basic chemistry of graphene is very interesting because of all of its possible applications. First of all, since the bonding is in a hexagonal lattice and the only element is carbon, each carbon bonds with 3 other carbon atoms, forming an sp2 hybridization. This then allows for a pi bond because there will be a double bond in order for the carbon to fill its electronic shell. The only problem is that there are 3 equally efficient ways to put the double bond on from each carbon atom. These resonance structures cause a delocalization of the pi bond, making graphene very conductive of electricity because it has a very high mean free path. The average bond angle around the 3 surrounding carbons is 120 degrees, but it varies slightly as the pi bond shifts. The average carbon-to-carbon covalent bond is about 0.142 nanometers in length, and since the carbon density of graphene is so high, it makes graphene a very strong material for its minuscule weight at 1 atom thick. Currently, scientists are experimenting with adding an element to bond on either side of the 2-dimensional structure. There has not been much success with this yet because of the formation of an sp3 hybridized carbon lattice, which is predicted to eliminate the conducting pi bonds and induce an energy band gap, making the conductivity suffer. Graphene isn't being used commercially yet because of the difficulty to mass produce. Physical exfoliation, such as the Scotch tape method, is the only way currently to consistently get high-grade graphene. Researchers at universities, such as Manchester University, are now experimenting with new ways to mass produce graphene chemically, because physical exfoliation consumes a considerable amount of time for very small quantities. Chemical exfoliation is still being developed currently because graphene is usually produced chemically by removing the functional groups from graphene oxide, and this is problematic because of the occurrence of fault lines and cracks in graphite, which leads to the unzipping of the graphite lattice during the removal of the oxygen. This produces graphene that is much weaker than it should be, and unreliable when used for commercial applications such as flexible touchscreens.